How are you everybody? How are you today? This is the fourth lecture in our course Econometrics. This is the course for a fourth year Statistics Department English section at Banha University 2020. This is a fourth lecture related to linear regression analysis, and it's a very important lecture in our course. Linear regression analysis. What the meaning by linear regression analysis? What is the linear regression analysis equation? What is the constant? What is the slope of linear regression analysis? In this lecture, we will explain everything about linear regression analysis by details. We will begin our lecture by simple linear regression, in which there are only two variables of interest in the regression equation. For example, weight and height, or force used and distance stretched. After developing tuition for this setting, we will then turn our attention to multiple linear regression, where there are more variables. While some of the equations in this chapter might be little, it's important to keep in your mind that as a user of statistics, the most important thing is to understand their uses and limitations. Toward this end, make sure not to get bogged down in the details of the equation, but instead focus on understanding how they fit into the big picture. Simple linear regression. We are going to fit a line y equal beta 0 plus beta 1x to our data. Here x is called the independent variable or predictor variable, and y is called the dependent variable on x, the independent variable, obviously, or response variable. Before we talk about how to do the fit, let's take a closer look at the important quantities from the fit. Beta 1 is the slope of the line. This is one of the most important quantities in any linear regression analysis. Beta 1 is the slope of the line, and this is one of the most important quantities in any linear regression analysis. A value very close to 0 indicates little to no relation. If beta 0 very close to 0, there is no any relationship. Large positive or negative value indicate large positive or negative relationship respectively. For our Hawk law example earlier, the slope is the sparing constant. Beta 0 is the intercept of the line. In order to actually fit a line, we will start with a way to quantify how good a line is. We will then use this to fit the best line we can. One way to quantify a line goodness is to propose a probabilistic model that generates data from lines. Then the best line is the one for which data generated from the line is most likely. This is a commonly used technique in statistics, proposing a probabilistic model and using the probability of data to evaluate how good a particular model is. Let's make this more concert. A probabilistic model for linear related data. We observe it paired data point x1, y1, x2, y2 up to xn, yn, where we assume that as a function of xi, each y1 or each yi is generated by using some true underlying line y equal beta 0 plus beta 1x z. We evaluate at xi and then adding some Gaussian noise formally yi equal beta 0 plus beta 1xi plus epsilon I. This is the first equation in our linear regression problem. Yi equal beta 0 plus beta 1xi plus epsilon I. This is the Gaussian noise, or the epsilon, or the error of observation, or error between observations. Here, the noise epsilon I or the error epsilon I represents the fact that our data won't fit the model perfectly. We will model epsilon I as big and Gaussian, epsilon distributed as normal, 0 and sigma square. This is the normal distribution. Note that the intercept beta 0 and slope beta 1 and the noise variance sigma square are all treated as fixed, i.e. deterministic, but unknown quantities. Solving for the fit least square regression. Assuming this is actually how the data x1, y1, xn, yn we observe are generated, then it turns out that we can find the line for which the probability of the data is highest by solving the following optimization problem. Minimization beta 0 beta 1 from summation I from 1 to ny I beta 0 plus beta 1 xi to the power 2, where minimum beta 0 beta 1 means minimize over beta 0 and beta 1. This is known as least square linear regression problem. This is called least square. Least square is very important topic in solving linear regression analysis. So that least square linear regression problem is known as least square linear regression problem to solve the linear regression or regression problem. Given a set of points, the solution is when we solve the equation number 2 by minimizing over beta 0 and beta 1, we must find beta 1 hat and beta 0 hat, and r beta 1 hat in equation number 3, r in equation number 4, beta 0 in equation number 5. Where x bar, y bar, x and sy are the sample means and the standard deviation for x values and y values respectively, and r is the correlation coefficient function. R equal 1 over n minus 1 summation I from 1 to n xi minus x bar over sxy I minus y bar over sy. This is the equation number 6 in our lecture and the last equation in our lecture, and in the next section we will continue our speaking about linear regression analysis, linear regression model, and about beta 0 and beta 1 and the correlation coefficient R. See you in the next lecture. Thank you for everybody. Thank you for everybody. See you in the next lecture in the faculty and on the faculty website. Thank you for everybody.